before I start, I'll just reject the dichotomy of applied versus basic science. I think that there are many, many pressing environmental questions for which there are a lot of basic science questions we haven't bothered to answer. And I hope I'll make that case to you today that there's a lot of simple questions we've left behind because they're not mechanistic and basic enough for us, but yet they're still really interesting. And a lot of pure ivory tower science questions can grow out of them. So I'm going to talk today about the most extreme form of watershed land use change that I have yet studied. And I think we can all agree that when you actually remove the entire mountaintop and throw it in the valley as a result of mountaintop mining, you've had a pretty extreme and profound effect on watersheds. This is the logical extension, I suppose, of questions that I've been asking since I got interested in ecology. Questions like, how do human activities in watersheds affect water quality, the things that come out of watersheds? How far downstream are the effects that happen on the landscape propagated through the river network? How long do effects persist once the impact ceases? And then a lot of my current work is thinking about what actions are effective at preventing and reversing water quality degradation. Can we actively manage landscapes or riverscapes in ways that actually helps prevent, reverse, or actually improve conditions in those systems? And so today I'll talk about a specific case of watershed degradation, that of mountaintop mining. So just taking those questions and making them specific to mountaintop mining, our questions are, what happens to the rivers affected by mountaintop mining? How far downstream do those impacts propagate? And what are the cumulative impacts of many individual mining permits on Appalachian rivers regionally? These are questions that, we've been doing surface coal mining in the Appalachians since the early 1970s, and we don't really know the answer to them. So I think you could say that's an applied question. You could also say it's a basic science question we've left behind that we should have probably figured out by now. So I'll start by making sure I acknowledge that the work I'll talk about today is being done in collaboration with a huge number of people. I'll talk about our empirical on-the-ground research in Boone and Logan counties in West Virginia, and that's part of a large multidisciplinary project at Duke University, including toxicologists, geochemists, hydrologists, trying to understand on-the-ground impacts. And I'll talk about our regional data synthesis effort that began through work I was doing with Margaret Palmer, actually initiated coming out of us being asked to be expert witnesses in a court case and trying to gather the information that was necessary to actually have an informed opinion about questions that were central to that court case, and has now grown into something that a number of my students and colleagues at Duke are interested in. So the outline for my talk today, I want to talk very briefly about Appalachian, what a special place it is, and then I want to talk about mountaintop mining, because you've probably heard of it, but I want to make sure we're all on the same page about what mountaintop mining is and what it does to ecosystems. And then I want to talk about the water quality and ecological impacts of mountaintop mining at local and regional scales. And I should have asked at the beginning, can you hear me in the back? Okay, and you can just yell, do this if I start getting quiet. So what do I mean by the Central Appalachian? This is the Central Appalachian ecoregion as defined by USGS. We're looking at a region that's primarily in southern West Virginia, a little bit of eastern Kentucky, a little tiny bit of western Virginia, and just this northern piece of Tennessee. So it's largely a West Virginia, Kentucky ecoregion. And it's a really beautiful and special place. If you've ever been whitewater rafting in West Virginia, you'll know that this is a beautiful landscape, ancient geologic formations, unglaciated, long periods of time for evolution to act in this topographically diverse landscape. And so it's a really beautiful place, but also a very biodiverse place. This is Nature Serves mapping of basically hotspots of rarity-weighted richness for critically imperiled species. And you can see that, as you probably already know, that the Appalachians are a real hotspot for biodiversity. Things like cerulean warblers are particularly of interest in the Central Appalachians, and of course it's a global biodiversity hotspot for salamanders. This is perhaps even more extreme if we think about aquatic diversity in this landscape. So these are basins identified by NatureServe, once again, as hotspots for at-risk fish and mussel species. And again, you see that the central and southern Appalachians are hotspots for the diversity of aquatic species. So this beautiful and biodiverse landscape is sitting on top of very rich reserves of energy in the form of coal. So these are the maps of coal reserves in the United States. You guys have probably heard a lot more about coal extraction just north of you in Wyoming. I'm going to talk about coal extraction here in the Central Appalachians. So let's talk about the process of mountaintop mining and what's involved. I'll just walk you through the stages. Of course, the first thing, what you're trying to do basically is to get at coal seams that are not accessible by traditional underground mining because they're fairly shallow. They're usually within 300 meters of the soil surface, and so you can't build your traditional underground tunnels to get to that coal. So the way to get it is to remove all the overlying rock and soil. So step one in getting to those surface coal layers is, of course, to remove the forest. It's estimated that by 2012, the area that will have been deforested by mountaintop mining and the forest state study area has been projected to be about 5,700 square kilometers. It's the largest form of land use change in the Central Appalachians. In this region, population is actually declining. People are moving away. And so development is not really increasing. This is the big land use change. And so that's about 4 to 5% of the entire land area of the Central Appalachians that's going into mining or mining adjacent land use change. So after the forests are removed, the next thing that happens is explosives are used to remove topsoil and overlying rock from coal strata. And so you'll generate basically what was a ridge is now you've moved away, this hill slope, and you can now see these coal seams buried within this carbonate bedrock. And so the job of coal mining is then to scrape out that coal, remove the next layer of overlying rock, and continue until you've basically worked your way around, completely around a mountain. So you'll see when you go up to West Virginia, you'll see mountains that look kind of like Devil's Tower. You'll go back a few months later, they'll look like a skinnier Devil's Tower. You go back a few months later and they'll be gone. And the big problem, the big environmental problem after you've lost these forests is that you generate enormous amounts of waste rock. So all of the stuff you had to move out of your way to get at the coal has to be put somewhere so you can keep mining. And so the best and most obvious place to dispose of it is in adjacent valleys. And that's how we get mountaintop mining and valley fills. You push the fill out of the way to access more of the mountain slope. And so this is just showing upper coal seams being removed and the spoils being placed in adjacent valleys, generating pretty immense valley fills where sections of stream are buried under hundreds of meters of rock spoil. And that's just, nobody argues about this environmental impact. That's an absolute loss of headwater stream ecosystems in the region. The scale of mining is almost, it's just pretty hard to wrap your mind around until you actually go out there. This is a drag line. These are about 40 stories tall. These are large excavators alongside it for scale. And each of these can remove 40 tons of material in each bucket load. So the scale and the speed with which you can chew through a mountainside is pretty remarkable. And indeed, it's the development of these large machines that's really accelerated the rate and the size and the scale of mining in the region. Okay, and so then after all of this material is removed, the regrading of the spoil begins and excavation can continue in other parts of the mine. So I like this picture here because it sort of shows the different parts of an active mine site. You have here a reclaimed valley fill. You have an active mined area. You can see they're going around that ridge, removing it. And then you have areas that are in the process of reclamation upstream. So most mines will be sort of moving slowly through a larger watershed, working their way from valley to valley. So it has become a remarkably efficient process by which this kind of mountainous landscape is converted into an economically valuable energy resource and leaves behind a very dramatically altered landscape. And that increase has really been exponential. Changes in the definition of a number of environmental rules, particularly during the Bush administration, really led to a dramatic increase in the number of permits that were being granted for mining and the size of individual mines that were being permitted. And so this just shows this exponential increase in new acres disturbed based on permit file data since the mid-1960s. And as I said, the size of individual mines is also increasing. So there's more permits being granted and the individual mine permits are larger. This shows the mean size of valley fills since 1985 to 2010. And so this is a really dramatic impact on the landscape. And we're interested not just in what's lost in actual mines, but what is generated in terms of waste downstream. Because this landscape is going to generate a whole suite of chemicals and sediments that then are transported into the river network. And unlike a lot of other places where you're doing surface coal mining, you are actually putting that waste directly into the river network. You're not isolating this hydrologically at all from the river system. So just to give you a sense of scale, by 2002, when the EPA completed their environmental impact statement, 2% of all of the streams in the Central Appalachian region had been filled. That's buried beneath valley fills. And 3.2% of the land surface had been converted to active or reclaimed surface mines. Just this past year, EPA came out with a new sort of summary of mountaintop mining activity, and they projected, based on already granted permits, that by this year, 4% of all the streams in this landscape will be filled, and 6% of the entire land area will be mined. So this is a dramatic change. And so how does this happen? What are the rules that govern this activity? So there's a couple of important rules that I want to make sure we're sort of clear on before I go forward. One is the Surface Mining Control and Reclamation Act, which was passed in 1977, which says you have to put the landscape back in the approximate contours you found it. It's sort of a funny, leave it like you found it kind of rule. This is actually a picture from the director of the Office of Surface Mining reporting on his helicopter flight over the region 2 years ago. And here's an unmined area, and here's a fully reclaimed area. And you can see it's a pretty different landscape. They used to, before SMACRA, mines were pretty small, and they used to just dump fill anywhere, and it was pretty unconsolidated. They didn't do a lot of post-mining movement of the fill. And then the other important rule is the compliance with the Clean Water Act, Section 404, which prevents putting fill into streams. And so this is accomplished by mining companies. They have to get a 404 permit from the Army Corps of Engineers, in which they say, well, yes, we're filling however many miles of stream each individual mine will fill, but it's okay because we're going to replace that number of impacted miles by creating stream elsewhere. And so this is an Appalachian stream that was slated to be filled. This is a created stream 15 years post-reclamation. And if you can't see the water, it's not your fault. There isn't any surface water in that photograph. And that's a real problem. Most of the time, the created streams that are being built are on top of old surface mines on basically a giant valley full of rocks, and it's really hard to get a channel that's going to hold water in that kind of landscape, as any hydrologist will tell you. So, as I said, when mining is completed, this mine will be regraded and revegetated. Until last year, from the time SMACRA was passed until about 2 years ago, that usually meant hydroseeding with non-native grasses. And so you have a landscape of, it's better than an active surface mine. You've got a recontoured landscape with hydroseeded grasses, and that does prevent sediment runoff, but it doesn't help you get very far back towards a forest ecosystem. You also tend to have, in the larger mines, very large slurry impoundments on the tops of the hills as well, where they've been washing coal before they ship it off to impoundment. So you have large impoundments of very chemically problematic water sitting up on top of a lot of these mines. And so you can actually go into the mine permit files, and I don't know how well you'll be able to see this, but I think it's pretty interesting to see what recontouring means in this landscape. So the original contours of this particular fill are shown here in this dark dashed line, and the proposed regrading that's going to put back the approximate contour is shown in this red line. So you can see that you're taking a topographically complex landscape and really flattening it out. It has some hills, but it's a pretty changed system. Those reclaimed watersheds don't appear to grow trees very well. This is from that original 2003 EIS work by Steve Handel, where he went out to a whole bunch of different mines that had been reclaimed as long as 24 years prior to the survey. This is the stem density in about 20 reference forests that were adjacent to mines, and this is the stem density of woody plants on reclaimed mines. So you can see really very, very limited recovery. You might say no recovery of woody trees. The exception are these really old mines that were done on very small pre-SMACRA mines where they had unconsolidated fill. And it does seem that trees actually do a better job growing when you don't compact the surface, which is an interesting issue. So there's some pretty big carbon implications of this at the landscape scale. This nice paper in ES&T last year by Fox and Campbell estimated that 0.71 teragrams of carbon per year being removed as soil and 1.7 teragrams of carbon per year being removed as the non-soil carbon pool. So a pretty dramatic change in the carbon stocks in this landscape. So the way this is argued in court cases and by mining companies is that this is a good trade-off environmentally, because you're creating a landscape that is, and this is a beautiful picture of a man standing in a reclaim mine, and you can see several more reclaim mines off in the horizon. They suggest that there are a lot of economic opportunities provided by making flat land in this landscape. This is a golf course that is about 120 miles from the nearest town. And it's not widely used except by mining executives, and all around it you can see other mines where they're actively creating new surface mines. And this is a Walmart that's built up against a high wall. So it's true that a few of these pieces of property are being converted into some sort of economically valuable land use, but there's not really a demand for 5% of the land area as flat land surface. So it's an interesting issue. Right, so the mining companies say that mining operations provide an opportunity to create economically valuable level land for all kinds of projects. Okay, but I'm really interested in the aquatic impact. So then what are the consequences, not just for the streams that are filled, but for the streams downstream? And let's just talk a little bit about the extent to which stream creation can compensate for the loss of a headwater Appalachian stream. So a headwater Appalachian stream is going to be a pretty interesting and diverse place. It might not have water flowing all year round, but it's going to be home to a pretty enormous variety of species. And it's unlikely that creating streams on top of old valley fills that are full of water that's coming off of these surfaces is going to support the same kind of community that's here. And indeed, a number of court cases have come to that same conclusion. In a court case back in 2007, Judge Chambers, who's a federal district court's judge, ruled that the Corps has no valid method for measuring the environmental harm from filling streams with mining waste, nor any scientific or rational basis for claiming that it can mitigate that harm. And yet it's central to every single permit application that the mining company make the case that they are not leading to any net loss of stream miles. So you can't get a permit unless you can document you're going to create a stream somewhere else that's going to be just as good as the one you've lost. The third piece of legislation that you have to be concerned with, there are others, but these are the three most important from the environmental standpoint, is compliance with the Clean Water Act or 303 permitting. So most mining permit applications will suggest that there is no downstream impact of mines. There's no off-site impacts. And yet, we frequently see very dramatic and obvious impacts. This is a large slurry impoundment release where you can see it's black water. It's just basically coal dust slurry moving through a river system. This is basically a carbonate-rich sedimentation in a valley fill in West Virginia. Here's an iron-rich precipitates in another valley fill. Here's a stream which is really interesting where all of the leaves are basically just cemented into the bed from carbonate materials. It's an interesting kind of drainage that's very different from acid mine drainage, which you may be more familiar with. In this landscape, we're really thinking about alkaline mine drainage. And the way this works is that you've got your classic pyrite problem that's central to many, many different mining water quality issues. Or pyrite that was formed back when these coal deposits were in wetlands, when reduced sulfur bound with iron to make pyrite minerals. When that gets exposed to oxygen, you have the release of iron and sulfuric acid from the coal mineral. And if you're in a lot of the mines in Pennsylvania, a lot of underground mines, a lot of the mines around here, you're going to see that generating acid mine drainage. But because you're doing this in this large landscape of carbonate rock, and you're basically creating debris, coal debris, in this landscape of very fragmented carbonate, what happens is that sulfuric acid is neutralized in reaction with carbonate bedrock. And what comes out of valley fills has a lot of sulfate, and that's balanced with calcium and magnesium. So you have actually alkaline mine drainage. The pH can go up a whole unit. So you may have these neutral streams going up to a pH of 8, and they'll be full of a variety of base cations. And often that will come along with a number of trace metals. Okay, so let's get to some data. What actually happens to downstream ecosystems? So it's not as if there's been no work on this. We know that there are significant deformities of fish in a number of reservoirs downstream of mines. We know that we see these dramatic and very colorful precipitates. And there's been a fair amount of work about the biological impacts directly downstream of a valley fill. So this is a valley fill in the Hobet Mine complex. I don't know if you can see the liquid here, but it looks like milk because it's so full of carbonates. This is a really influential study by Greg Palm at the US EPA that came out in 2008, where he compared 8 streams below valley fills, within a mile of valley fills, and 8 matched streams from unmined watersheds. And he saw that this is the total number of aquatic insect genera, significantly lower in the filled than in the unfilled and the unmined streams. This is the number of mayfly, caddisfly, and stonefly genera, more sensitive taxa, also significantly lower in the filled streams. And then what was really dramatic is a complete loss of mayflies. These are Ephemeroptera genera. Complete loss of these dominant grazers that make up, say, 80% of the abundance of organisms in reference streams. So a pretty dramatic shift in composition in these systems. These are slides that Greg provided to me that show you a characteristic fauna of an unmined headwater stream and the characteristic fauna of a valley fill impacted stream. And those of you that aren't aquatic people, you might think, well, there's brown bugs in both of those pictures. So I thought, just to make this a little clearer, this is like if you went out to a coral reef and you saw this, you'd be really excited. And if you just saw a bunch of anchovies, you'd be less excited. These are the things that you find below, wastewater effluent ponds. These are the things that live everywhere, no matter what you do to them. It's a whole series of chironomid midges, really, really tolerant caddisflies, and a whole bunch of different true flies. So we use these all the time to assess water quality, right? And the loss of this great diversity of mayflies that are doing all this grazing and stoneflies that do the work of turning sticks and leaves into fish food is a dramatic change in the food webs of these systems. So one of the first things that Margaret Palmer and I did when we first got involved in some of these questions was just try to synthesize existing data from the state of West Virginia that has their stream monitoring program. We got data from 1,058 streams in West Virginia in this mountain bioregion, and we used, in this case, sulfate as a proxy for mining activity. So many documents suggest that if you have sulfate concentrations over 50 milligrams per liter, you have to have mining in the watershed. You would never see that without some sort of coal mining effect. So we just used bins of sulfate concentrations here, and we found that, in fact, you saw an increase in total selenium, total iron, total aluminum, and total manganese that increased predictably with increases in sulfate concentration. And along with that, you saw a decline in the total number of insect genera. This biological indicator that's used is a narrative criteria. So this is how the state of West Virginia assesses whether a stream is biologically impaired. They use this indicator score. This is the number of sensitive taxa, and this is the number of mayfly genera. So you see this strong effect that's true regionally. This is across all of these streams all over West Virginia, not collected for this purpose. So it looks like you definitely have an extension of this impact. However, this is a little bit unsatisfying because we're using a proxy here. And what we really wanted to do was actually try and go out into the landscape and say, well, can we link biological degradation or water quality shifts directly to the amount of mining that's going on in the landscape? And so we chose to ask that question in the Hobet Mine complex, which is in the Mud River of West Virginia. I'm showing you NASA photography back from 1984, where you can see the expansion of this, which is the largest contiguous surface coal mine in the region. It's pretty well known. This particular fill was the largest fill permit ever granted for a third-order stream. And this region right here has been mined since the last photograph was taken. It's being actively mined right now. It's one of the last permits granted. So this is a pretty tremendous mine footprint, and what's interesting about it from a scientific standpoint is that the Mud River originates here, flows right along this road, and then flows through this mine. So you can actually go through and look at how each of the tributary inputs from this mine complex affects the water quality of that stream. So I should just say, this is by 2009, 40 square kilometers have been mined, and that has probably gone up by another 5 square kilometers at this point, and 40% of the tributaries to Upper Mud have been filled. To give you a sense of scale, of overlaying that profile on top of the city of Denver, which I'm not that familiar with, but if you are, here's Glendale, here's Wheat Ridge, here's Lakewood, here's downtown Denver. You can see it's a pretty big footprint. This is what it looks like when you fly over it in a helicopter. A very, very dramatically altered landscape. So you can kind of imagine the amount of bicarbonate that's going to be running off that landscape. So here's our study design. The sampling points are shown here along the main stem of the Mud River, along with all these tributary inputs that are coming in to the system that are shown in triangles. This figure shows an aerial photograph, and all these little circles are individual pollution discharge elimination permits. So there's over 100 separate water pollution permits that have been granted in this landscape, or variances, if you will. So we've sampled an enormous number of things, basically monthly for the last couple of years, and I'm just going to show you the first set of results. So again, orient yourself. You're going from upstream to downstream, and that on this map, that'll be from here down. Each of these red triangles is a point where a valley fill impacted tributary comes in. And I think it'd be hard to be much clearer about what the impacts of the cumulative loading of new mining impacted tributaries are in this landscape. So this is conductivity. It's a measure of the total electrical conductance of water, which is a proxy for its ionic content. And so as you increase calcium, magnesium, sulfate, bicarbonate, conductivity also increases. And what you can see is that we have conductivity less than 100 microsiemens in these first two sites, and as soon as that first valley fill comes in, we get an increase. Now, month to month, that varies depending on what the flow is. So in low flow in October, you have really high conductivity. In the highest flow after a storm in July, you have the lowest. But no matter what, you see this dramatic increase. And here's sulfate, and here's selenium. And I'll just put some lines on here to make this more clear. This line here shows you the conductivity guidance recently issued by the EPA, suggesting that this is the conductivity you must attain to be protective of aquatic life in this region. And you can see as soon as that first valley fill comes in, we typically exceed that conductivity for large periods of the year. We see that here I'm showing you the chronic toxicity threshold for selenium for fish, and that we typically exceed that. And by the time you've gotten down to the last sampling point in this river, you can be as much as 4 or 5 times above that chronic toxicity threshold. So if you look at the average concentration of conductivity, sulfate, or selenium in this river and compare that to the total areal extent of the watershed upstream of that point, sampling point mined, you'll see that we can explain a tremendous amount of that variation purely based on the total amount of mined area in the landscape. And one of the interesting things in this, this map is that this set of mines here was reclaimed and completely released more than 15 years ago. So one of the questions that we have within this is how does that reclamation change the pollution signal? And it's too little data to conclude anything with any certainty, but it's certainly intriguing. This is connectivity for upstream reference systems and also connectivity on another branch of Mud River that has no mining on it. Here are all the actively mined tributaries, all 6 of them, and here are the reclaimed tributaries. You can see in terms of connectivity, there's no decline in that signal, even 15 years post-reclamation, no decline in the sulfate signal. It is interesting that selenium content in those 2 reclaimed mines is lower. Note in these valley fills, every single one of them is above that chronic toxicity threshold on all dates. Here, even one of the reclaimed mines is above it. We don't know if this is because of time or if it's because of differences in the mining approaches that were used 20 years ago when these things were mined. Did they get the same geologic layers as they're getting today? And that's something that we're pursuing. We also found in limited efforts to sample fish in the Mud River dramatic instances of deformities. So in a collection of 20 fish, 5 had significant deformities of basically large lips or scoliosis of the spine, both symptoms of chronic selenium exposure. So clearly a strong influence. So from this local study, I think we can say pretty clearly that we're seeing a dramatic and cumulative impact of mining on the water quality. We don't have great biological data, but we can certainly see that we're getting biomagnification at the food web. That biological information is coming, so stay tuned. But certainly strong evidence that there's a cumulative effect. It's interesting that 10 miles below the last piece of the Hobet mine is a reservoir where people fish. And in that reservoir, they've seen some of the highest deformity rates of bluegill that have ever been measured. And yet, there's nothing posted there. You can fish there all you like. So it's an interesting landscape. We know that we're seeing selenium concentrations over the chronic toxicity threshold and conductivity above that EPA threshold, even below that reservoir, more than 10 kilometers downstream. So pretty extensive longitudinal impact. Okay, but that's just one site. So let's go back to these questions. The other thing, and let's think about the biological impacts more broadly at a regional scale. This is something we've been working on for a long time. As I said, this original analysis we did in a science paper back in 2010 was a little bit unsatisfying because we had to use this proxy for mining. But after this was published, I got a call out of the blue from a group that had actually mapped surface mining activity throughout the Central Appalachians every 10 years back to 1975. So they gave us access to these GIS layers, and we were able to, for the first time, to estimate the cumulative impact back to 1975 of mining in watersheds throughout the region. So we chose a 19,000 square kilometer study area in southern West Virginia where we had extensive bug data. All of these triangles are points where the state of West Virginia has reported stream benthic invertebrate and water quality data. We were to delineate the watershed to each of those points and calculate the amount of mining that occurred in each of those watersheds back to 1975. All of the green points here represent state reference sites. We had 240 reference streams in the state and 223 watersheds where we had stream biota identified to genus, stream chemistry, and we screened out all the watersheds that had significant amounts of development in them to avoid any sort of confounding effects. So when we go to this data set, which is a little bit a better way to look at the mining impact, we see in fact that the percent of mining in the watershed is a pretty good predictor of the total conductivity in the draining stream. Here are our 240 reference watersheds. The highest conductivity you ever achieved there is 240. The mean is about 80. The amount of mining in the watershed explains 50% of the variation in conductivity across sites. So we see that. And then that really is a mining signal. We see that conductivity is itself extremely highly correlated with sulfate concentrations, and this is conductivity correlated with base cations, calcium, and magnesium. So we're seeing this as an alkaline mine drainage signal. So we wanted to know, okay, well, we know that mining is really closely associated with these water quality problems. This suggests that you're getting a water quality problem that is propagating well downstream of the mines themselves. Because remember, we can have, oops, go back. Watersheds that have this incredibly high conductivity that have only 5% of their surface mined. That means you're going to be pretty far downstream of the mining impact to get that much dilution. So we've been looking at biological data from all these streams to try to detect, is there a threshold response to this signal? And we can look at the mining signal directly. We can look at the conductivity generated from mining or the sulfate generated from mining. And we'll just walk you through this graph. This is the number of intolerant aquatic insect species here on the y-axis versus each of these gradients. We're using a generalized additive model, which is a classic approach for looking at threshold responses. And I'm comparing it here to the 25th to 75th quantile of those 240 reference streams. So you can see it doesn't take much mining until you generally find a really depauperate community in these systems. And so we can take this and look at actually legal impairment thresholds. So here, this is the West Virginia Stream Condition Index. This is part of what gets a stream listed on the 303D list of polluted rivers. The dark red line here is at 62, which was the number that the consulting firm that was asked to develop it by the state of West Virginia suggested should be the impairment threshold. That was what they used for a while until they found that that was difficult to achieve, and so the new narrative criteria that's in the legal standards is at 60. And you can see that makes a big difference in how you interpret a threshold, right? Because we see a very low threshold for that upper impairment, where we said that our model crosses that upper threshold pretty early on, but we have considerable uncertainty as we get into whiskey scores of 60 or so. This is a genus-based macroinvertebrate score, which is what most aquatic ecologists would suggest to be a better metric to use than a family-based metric, because you have a lot more biological information. You're not mixing tolerant genera and intolerant genera within your metric. And we see here that we have a very dramatic drop-off in both of these scores with all three of these gradients. So we can take this threshold, our model's estimate of where we cross these thresholds, and then we can go back to our maps and map the total river network length that falls above each of those thresholds. So for the whiskey score, we estimate that once 5.6% of the watershed area is mined, you cross that upper threshold. For the glimpse score, we estimate that when 0.2% of the watershed is mined, you cross that threshold. We can then go back to our river network. We can calculate for every single pixel in the entire hydrography data set how much of the upstream area is mined. And so what you're seeing here in red is all the river network that is draining a watershed that has at least 5.6% of its watershed area mined. And the sort of yellowish beige color shows you below that those that have only more than 0.2% of their watershed mined. So we can then sum that up and estimate that in this region, somewhere between, once we get to 2005, somewhere between 15 and 30% of the entire river network of this region is affected by a land use change that's affecting 5% of the surface area. And just to give you a sense of what that looks like on the ground, here's a cutout of just one of those small sub-watersheds looking at the mining in gray here. The mine footprints are mapped in gray. You can see the expansion of mining in this small watershed from 1976 to 2005, and the propagation of this signal, because we don't have any evidence that signal declines with time, no evidence in our synthesis data, no evidence in our empirical data. So we're just adding new conductivity, salinity, salt loads into this system through time and chemically affecting a larger and larger extent of this entire network. So what can we conclude so far? I think we've begun to answer some pretty basic questions, which are very useful when you're having a conversation with people at the EPA about whether or not they should worry about cumulative impacts or not, because that's currently not part of the discussion at all. I think we can say safely yes. I think we can also make a pretty clear case that the water quality impacts do, in fact, move off permit boundaries. We also can make a pretty clear case that reclamation is not effectively reversing those effects. So individual mountaintop mining sites are massive in scale. They lead to an absolute loss of stream length and significant degradation of water quality that extends well downstream of those permit boundaries. The effects appear to persist, although this question needs a lot more work. We see slow or no forest regrowth, and we see water quality that's degraded for at least decades, perhaps longer. Each new mine is adding new pollutant loads and expanding those impacts further downstream. So that's sort of the work of a couple of years now to try to put together what, you may say, that's a really simple story, and maybe you should have known that before. And I guess when I started working on this, when I was first asked these questions, I assumed that I could go to the literature and find these things out. But it just hasn't been done. And it needed to be done first so we could get to some more interesting questions. And I want to end today by talking about some of the next steps, the things that we're thinking about as new questions that come off of this as background. And I'll just give a little bit of a teaser in the hopes that we can have a conversation about it. The first is really thinking about what is the land and river disturbance footprint per BTU of mountaintop mining. So we can actually calculate the amount of coal being produced per area disturbed, and we can link the amount of area disturbed to the amount of river network length degraded. So that becomes interesting, right? We can now actually say, here's the footprint, here's the environmental cost of that unit of coal, which becomes really interesting because then you could actually use this information to compare that environmental footprint to traditional underground mining or to other sources of energy like hydraulic fracturing, which is becoming an increasingly important aspect in this region. I think this is something we don't do very well as ecologists, is actually not just say, hey, this form of resource extraction is bad. We should spend more time thinking about how does this form of resource extraction compare to other forms of resource extraction and start building a language or a set of metrics which allow us to do that in a better and more effective way. A really important follow-up question to the work that we've done in the Hobet mine is to expand our view to think about how the water quality impacts of surface coal mining change over time and how they may differ by regulatory era. So my student Matt Ross has just begun his Ph.D. He's identified 100 watersheds that range in, that are sort of bend by when they were mined. So we have watersheds that were mined and released back in 1975, a whole series that were mined between 1980 and 1990, and a whole bunch of active mines. And we really want to see, is the signal coming off of those differentially reclaimed landscapes different in any predictable way? It's kind of interesting because you can actually get very detailed permit files that describe the actual way in which fills were constructed. And we hope we can begin to use that to predict whether you're going to see larger storms, larger storm-derived pollutants, changes in flow, as well as changes in chemical signals. So we're just beginning that work, but I think that's a really important piece of the overall story. we've begun to think about whether the effects on biota propagate upstream as well as downstream. And there's a couple ways this might happen. We've been able to identify throughout our river network how many headwater streams are unmined themselves but sit upstream of mining impacts. So you could begin to think of chemical fragmentation in this landscape, which could be important, particularly for species that have to disperse through the river network. You can imagine that if you're a fish trying to get here that is sensitive to the high ionic strength and high trace metal concentrations, you're going to have to swim many kilometers to be able to access that headwater system. And so we're interested to know whether the communities in these chemically stranded headwaters are in fact distinct from headwaters that are more connected to contiguous high-quality water flow. And so the impact might actually expand beyond this downstream impact. We're also interested in understanding whether microbial communities are responding in similar ways to the macrobiota in these systems. So we know that the macrobiota respond with a significant loss in sensitive taxa. We don't yet know what microbes do. We're just beginning that work. In fact, we have a bunch of data just sent to the sequencer, but I'm going to guess that the answer is going to be not quite the same. This is some really early preliminary data looking at average connectivity across that Hobet mine site versus the number of bacteria OTUs. So we see an increase in, if anything, an increase in the diversity of taxa in those systems. What that means functionally, who the heck knows at this point? We are curious to see how functional groups of microbes are changing in response to this very strong chemical gradient. And that leads to this final question, which is, do altered stream communities, be they these macroinvertebrate communities or microbial communities, lead to altered ecosystem functions? So are we changing the way these systems work in a fundamental way? We have to know at some level that's got to be true, but how are we changing, and what does that mean for the diversity of these systems through time and their ability to recover? And I think I'll stop there and take any questions. And thank you for your attention. Whoa, sorry. Questions? Yes.
Have you had any pushback from the mining companies?
Yes. He asked if I had, oh yeah, so the question was, have we had any pushback from the mining companies? And of course, the answer is yes. The issue, there's many legal and regulatory issues, and we've been having frequent conversations with EPA regulators about these issues. The EPA has made a strong push to put forth guidance that would stop any new permit granting in this landscape if the mining companies can't prove they won't exceed connectivities of 500. So far, there's no examples of that ever happening. So this would be pretty extreme. And right now, the EPA is being sued by the National Mining Association and the state of West Virginia for that guidance. And it really all hinges on the uncertainty around relationships like this. And so if you're an ecologist looking at this, you're probably focusing on the central tendency. But in the literature being put forward in this case, they're saying, look, there are some mined watersheds with good bug data. And look, there are unmined watersheds that have bad bugs. And focusing on the uncertainty. And so it's really interesting where uncertainty, which is going to be the case, particularly when your data set was not collected for this purpose, is really where all of the decision making is hinging right now. And it's an interesting place to engage as a scientist. You had a question?
What sort of flow change is happening in these regions? How's that changing?
Yeah, so Oliver Ferrari has a nice paper that came out a couple years ago on some recently reclaimed mines showing that they act very much like urban systems in that they're compacted and you get really high flashy flows. You definitely have a lot of anecdotal evidence from people that live in the region that streams that used to run dry every summer now flow year round. So I think we're definitely taking a lot of ephemeral streams and making them perennial because you've lost all that evapotranspiration in the watershed. The flooding part, there's a lot of anecdotal evidence that it's increasing large floods, but I think that really depends. Some watersheds set up a big storage pool of water, almost like an aquifer's being made in those watersheds, and they may only flush out if they have a lot of antecedent flow. And some are basically having a lot of surface runoff. So I think there's a lot of variability in how those things get put back together, and that's one of the things that we're trying to pursue in Matt Ross's dissertation work. because I think that's interesting, and implications for flood disturbance and for the timing of pollutant loads is going to differ a lot based on reconstruction. Yep.
So if you were giving advice for how you could get a reasonable amount of energy out of that system without destroying what's already there, is there some place where there's a close sweet spot you could do some stuff and the return cost-benefit ratio really works for you, or is it just a bad idea?
I think that's a really important question, and I wish there was more variability in what's being done out there so you could ask that. There are some people suggesting that there are new techniques where you could actually make sort of side cuts into hills and get at coal seams without moving all that overburden. I think that's an interesting approach that might have some benefits. There's been a lot of we won't do a fill in the stream, we'll do it 10 meters over in the valley. I don't think that works. I think you just have so much runoff coming off the watershed that whether that fill is 10 meters away from the stream or in the stream isn't really going to make a big difference. So we're probably better off thinking about ways to be less invasive and generate less overburden per unit coal. It's interesting too because underground mining is generating still more of the coal in this region. There still is a lot of underground coal. So I'm not taking a position on this because I really don't know the answer, but a number of environmental groups who are opposed to mountaintop mining would like to see more underground coal being generated. They're not really opposed to coal so much as this incredibly destructive kind of coal mining. Yep.
I remember during the 2008 election cycle, there was some articles about cleaner burning coal in West Virginia.
Yep.
Can you tell me a little bit about that?
That's a great question. So the question is clean coal, and you hear about clean coal all the time. Clean coal has nothing to do with getting it out of the ground and everything to do about trapping the pollutants as they come out of the smokestack. So you could have clean coal that's coming from a mountaintop mine. And I think that's a really interesting problem, that you're not thinking about the life cycle of that energy source. You're thinking about purely at the stage of burning. Leroy?
Emily, given the pretty clear biological, ecological effects of even a small amount of the watershed being mined, 5% or so, and given I guess the reality that standards are in obvious violation, is there any discussion, or what would you think about the idea that maybe this is, in some sense, just a consequence of our lifestyle and a more regional approach to conservation of the biodiversity of streams and other, these Appalachian landscapes might be worth thinking about, where you basically put certain watersheds just off limits and have sacrificed those, if you will.
Yeah, I think that's an interesting issue. I think we already do. I mean, the big mine counties are, there are a couple of counties that have already 15 to 20% of their land area in surface mines, so it's not distributed evenly. And the question is, well, should we just focus our energy there and just go ahead and get every bit of surface coal that we can get out of those regions in order to protect other regions? That's not really a scientific question, is it? That's a philosophical question, and I guess if you're thinking about biodiversity, we don't have that biodiversity map. So we don't really know what decision we're making. And it's interesting, TNC, they've done all these surveys of biodiversity. They wrote off several major watersheds in West Virginia. They said, we're not even going to bother measuring it because we're sure it's screwed up. But they've recently decided to get money to go out and actually figure out if that's true or not, which I think is a nice idea. So I guess to a certain extent, we've already decided to do triage. And the question is, should we continue? Well, I was going to say that's never going to work because that would mean you'd be choosing some mining companies who happen to own land in those places versus other mining companies. And so I think the economics would get in the way of making that as a purely scientific decision.
Are there any U.S. Forest Service lands in this area that are mined or off limits?
I don't know about that. So the right beside the Mud River system that I was talking about, there's a really large Forest Service land called the Big Ugly, which is actually really beautiful, and it has these gorgeous streams, and it's just been permitted to be mined. So I don't know exactly how that works and how they move the mineral rights around. Any other questions? Yeah.
evaluated for any of those watersheds? And if so, then has it been, could we look at it as an economic question, as you mentioned, the economics of the situation?
So the question was whether the economic services have been evaluated and whether you could use that as a way of forcing additional mitigation. So there's not, right now, there isn't really a market, right? So they've calculated the carbon cost, but that's not, I mean, that would be easy to pay off with a few days worth of coal, because carbon is still really cheap, even if you're in the voluntary market. There is this mitigation market, right, which is not really an economic market so much as you have to do some amount of river mitigation or wetlands mitigation to be able to get your permit. They could up that a lot. The problem is what they're doing is not having any effect at all, so doing more of it doesn't make a lot of sense. In fact, that's what you're seeing in a lot of the permits. They're saying, we know it'll probably take more than 5 years for this created stream to be as nice as the stream we filled, so we'll just do 15% more to compensate for that. And I'm not kidding, that's really what it says. So, but the idea of doing more of zero is still zero. So that's not really going to be an effective way of dealing with this. You could force other mitigation requirements that would make it more expensive, but it's not clear what they would be and how you would actually effectively mitigate for this kind of impact. So it's hard. Jill?
What about downstream drinking water quality? Are there effects on municipal supplies?
Yeah, so the Duke group has a big rural health initiative as part of our group, and we've just begun surveying drinking water wells in private residences for 200 people. That's started this winter and will go through the next summer, and they're in the process of analyzing that data. So we are looking to see if you're seeing that in water supply. Certainly just the salinity, the ionic strength itself is problematic for water treatment. And a lot of people in this region are on well water, though, so the bigger question is whether or not it's getting into their wells. There's been a lot of work by Michael Hendricks at West Virginia University on human health impacts. It's all correlative because all the health data is on county levels, not river basin levels. But he definitely has pretty strong evidence, about 6 papers in the last 2 years, showing higher incidence of a number of cancers and kidney disease in counties with mountaintop mining, even above counties that have a lot of underground mining. So and with women and children, not just the miners themselves. So there do seem to be some pretty strong circumstantial evidence that there's something going on. Whether it's a water quality thing or an air pollution thing is harder to say. But I think there's reason to think there are human health consequences of this. In the back.
You just touched on one issue that I'm curious about. I would imagine this form of mining creates a lot of atmospheric particulates.
Mm-hmm.
Has anyone looked at where it disperses and whether there's any atmospheric deposition of the same types of
Right.
other types of food?
So the question is about atmospheric deposition of dust, and there's a huge amount. The explosions generate huge amounts of dust, and the coal, moving all this coal around in these giant areas where they're washing and storing coal also generates a huge amount of coal dust. But there has been almost no work done on that at all. It's just crying out for someone to do it. If anybody here wants to go measure aerosols, it's really important. We've started some very limited dust collection, but I think to do that well, we need some really, really good chemists out there doing that kind of work. Michael Hendricks, the guy who's been doing the human health impacts, was so frustrated by the lack of data, he started handing out these little, I guess they're just particulate meters to people in towns that have been experiencing health issues or are concerned about health issues, and definitely reporting, downwind, particularly of coal processing plants, huge increases in the amount of particulates that are in the, so people are breathing in coal dust. Just by living downwind of those areas. Less clear what the mines themselves are doing. People complain a lot about dust in their houses and noise, but it's harder to know what's going on there. It's a good question, though. I guess here.
I'm just curious if there's any protected species being directly or indirectly affected by mining.
Is there any? Sorry, what kind of species?
Any protected species.
Are there any protected species being affected by mining? So, no. According to most permit files, there are no protected species. The big ones of concern in this region would be the cerulean warbler, which has a sort of a interior forest habitat, and it's definitely being affected. And then the salamanders, this incredible biodiversity of salamanders. And there's just, if you read a permit application, they'll say there are no protected species here. I don't know what level of rigor is done in actually making that assessment. I really don't know. I'm not saying it's bad. I have no idea. You want
Let's
to
just
pull it
take
off?
one more question and then let her off the hook.
Okay.
Here's what the mitigation of streams. I know that's a field that's still developing, but is there any discussion at regulatory level or other levels about other options for stream mitigation if this is going to continue, since it's clearly, as you said, zero?
So there's a experimental. Sorry. The question is there any progress in better river stream mitigation? And I guess the question is for what, right? So they're mitigating for habitat because they filled these streams. So you could mitigate for that by potentially improving stream habitat somewhere else that's not mined. But they're also supposed to be mitigating for water quality impacts. I can't actually think of any way in which restoring or changing a stream or building a stream is going to actually change the water quality impacts, particularly with these water quality issues, which are largely, mostly because they're so high in concentration, mostly traveling in conservative solutes in this system. So I don't have a good answer for that. If you have any good ideas, you should. There's a market for that. Thanks.
All right. Well, thanks again, Amy.